All right, so tonight there are three problems that we're going to work through. We have a two proportion tests, and that is from section 11.1. And we also have two different two-mean tests, one with summary and one with data. These are both from 11.3. So we'll go through those three. We'll talk a little bit about identifying the problem, setting up the problem, checking the conditions, and working in StatCrunch. Now, the tests that we do in these two sections, we don't cover a backup test for them, but the conditions are really important, not just outside in the real world, but also in the MyLab assignments. They're going to ask you for some of these calculations. So this will, we'll go through that in great detail. So the first problem, when I read through it, the first thing I notice here is I have two sets of sample data, X out of N, 46 out of 250 and 12 out of 150. The variable in both cases is categorical. You know, if we were trying to gather this data, we would ask the patient if they've gained 7% or more in weight during the trial, and their answer is going to be yes or no. So those are categories. And if we look at the claim, patients who take the medication, more likely is a measure of probability. Probabilities are proportions, are more likely to show weight gain than those who take a placebo. So we're comparing one group to another group. Everything here says to proportion. Now, the first step is you have to list what population 1 is going to be. And population 1 should always be the first group that's mentioned in the claim. And here, that's the group that are taking the medication. The reason that you want to use the first one in the claim, which isn't necessarily the first set of data that you have, is that the sign can be taken directly from the wording in the claim. If you switch the order around, you need to switch the sign around, and that gets a little confusing. The null hypothesis for a two proportion test, always P1 equals P2. And for H1, we're trying to figure out what sign goes between those two. Now, when we say that the people who take the medication are more likely to show the weight gain, more likely means greater than. One quick note. Oops, lost my sign, sorry. Greater than. One quick note here is that this is what we would consider to be a friendly sign. And what that means is that we don't have to worry about changing the wording in the claim when we get down to writing the conclusion. Right? The wording in the problem is the wording we can use. Second step, level of significance is given in the problem as 0.05. Third step, it looks like a two proportion test, but there are two conditions that we need to check for both the patients getting the medication and the patients getting the placebo. The first one, let's do this in red. The first one is that 20N condition. We multiply the sample size by 20, and then we have to make sure that the population size would be bigger than that. So these 250 patients, we don't know anything about them, so we can really consider them to be 250 people. And let me write medication, 250, oops. For the medication, sorry about that. 20 times 250 is 5,000 patients or people. And are there more than 5,000 people? Yeah, we know that that's true. Then we would do it for the placebo group. That's 20 times 150, that's 3,000 patients. And again, there are more than 3,000 people. So that condition is good. So the 20N condition works. The other condition, and by the way, the 20N condition is equivalent to saying that the sample is no more than 5% of the population size. And what that guarantees is that we have what we call an independent sample. What we picked for who we picked for one individual doesn't impact the chances of the other person showing weight gain or not. The second condition is to make sure that the distributions follow a bell curve. And that's by checking that X times N minus X divided by N is greater than or equal to 10 for each of the two samples. Now, in this case, this is listed in the book that way instead, but it's a lot harder to work out the arithmetic there and get an exact answer. So the fraction that I've given you, X times N minus X over N, that is exactly the same, but a lot easier to work with. In the first sample, X is the 46 out of N equals 250. So the way that I write this is I put the 46 on top, I put the 250 on the bottom, and then I just need to figure out what is 250 minus 46. And that is 204. So that's the arithmetic I need to work out. 46 times 204 over 250. And I can do that in the calculator. Fraction 46 times 204, denominator 250. And I get 37.5 and change. And that is bigger than 10. So that first one works. And then for the placebo group, we've got 12 out of 150. So I can do the same thing. In the fraction 12 over 150, and then subtract 150 minus 12 and put that here. That's 138. So we can work this out. 12 times 138 over 150. 12 times 138 over 150. And we've got 11.04. Now that's a lot smaller, but it's still bigger than 10. So both conditions here work. And what that tells me is that I can go ahead and finish this as a 2 proportion test. When I get to the calculations, I'm going to use stat, proportion stats, 2 sample, and summary. And those are the steps always for the 2 proportion test. Let me change the orientation here. I think it's going to crash. Okay, let me restart that. And while I'm doing that, I'm going to open up StatCrunch. I don't need any data for this problem. The iPad's almost open again. There we go. And what some students have some luck with is if you list population 1, the people with the medication, that was 46 out of 250, and you list population 2, the placebo, that was 12 out of 150. Then you've got those numbers there. It makes it easier when you get to StatCrunch. Stat, proportion, 2 sample with summary. The first group is 46 out of 250. The second group is 12 out of 150. We don't change the 0. So for all the tests in chapter 11, that 0 doesn't change, but the sign for HA, RH1, does need to change. And here it's got to be a greater than sign. And that's it. So you enter your first sample, your second sample, pick the right sign for HA, and you go. And here we've got Z equals 2.86. and the p-value is 0.0021. We compare that back to the level of significance, and that is a low p-value. Once we get to this point, all the tests are the same. What do we do with a low p-value when we get to the decision? Low p-value means we need to reject HO. Common issue for some students on this part is they'll just write reject, but you've got to tell me what you're rejecting. If you just write reject, it's not correct. So whether you say reject or fail to reject, it's got to be about HO. Now, when you reject HO, that means that there is sufficient evidence to support, and I'll allow you to use that abbreviation if you'd rather than writing it all out. That, and again, because I had a friendly sign in H1, I can copy the conclusion down directly from the problem. And that says, oh, I can't read them both at the same time. I'm sorry. That patients who take the medication are more likely to show significant weight gain than those who take a placebo. So in this problem, we had the strong decision, reject HO, which means we have the strong conclusion, there is enough evidence to support this. That means that we're saying that, yes, people that take this medication are more likely to show weight gain than people who don't. So that's saying that the medication causes weight gain, because this was a random experiment. We divided the patients into two groups of our choosing, whether they would get the medication or the placebo. And so now we can make a really strong conclusion saying that this causes that this medication causes an increase in weight gain. If we had had a high p-value, we failed to reject HO, then we didn't have enough evidence to prove that happened, but the low p-value helped us. All right, before we try the second problem, I'll open it up to questions. If you have a question, you can unmute yourself and ask it out loud. Any part of this is fine. If you'd rather, you can type your question into the chat and I can address that as well. So I'll give you a minute if you have any questions before we look to the second problem. All right, hearing none. Let's go ahead and take a look at problem 2. Researchers conducted a randomized double-blind. That means that the researchers and the people in the study didn't know who was getting the medication. So both the people running the experiment and the people taking part of the experiment don't know which group they're in. And this study was to measure the effects of a certain drug on patients diagnosed with bipolar disorder. They took 115 patients with this disorder and divided them into two groups. One received a daily dose of the medication, olanzapine, and the other group, they received a placebo. So 55 patients got the medication, 60 got the placebo. The effectiveness of the drug was measured with a total score with the net improvement recorded. So I've got two samples. Sample 1, we're told how many patients there are, N, there was 55. We're told the mean, that's X bar, and we're told the standard deviation, that's S. That's a summary of the first sample. And the second sample also has those 60 patients, mean of 8.1 points, standard deviation of 12.7 points. We have two sets of summary information for a numerical variable. So we have what we need for a two mean test. We just have to make sure that the claim matches that as well. And here we're comparing an experimental group. We're saying that that group has a larger mean improvement than a second group called the control group. So it's group versus group, two numerical variables, and two sets of summary. Mean, standard deviation, size. So everything here says two mean with summary. The one with summary is a little easier to do because there are fewer conditions to check. Step one, you have to list population number one. Again, that's true for every test from chapter 11. And population one should be the first group mentioned, and that's the experimental group. By letting them be population one, then I can use the wording larger mean to use the greater than sign when compared to population two. The null hypothesis for a two mean test, mu1 equals mu2. And like I was saying, H1 is going to be mu1 greater than mu2. Step two, level of significance 0.01 this time. And by the way, when you're doing an experiment involving a medication for a medication that you're going to sell, where there's a lot of liability, you want to make sure that you're not making a type 1 error. And so by lowering the level of significance to 0.01, now we're saying you're only going to make a mistake like that 1 out of 100 times, where at 5% or 0.05, that's 1 out of 20 times you'll make a mistake. And when you can get sued or somebody could get hurt or worse, you want to be more careful with that level of significance. Step three, it looks like a two mean test. The only conditions that we have to check, because it's with summary, is the 20N condition. So in both cases, again, these are just patients. So for the experimental group, 20 times 55 is 1,100 patients with bipolar disorder. Are there more than that? There are definitely more than 1,100 with that. And then for the placebo group, 20 times 60, that's 1,200. And there's more than that too. So the conditions work. We're ready to do our calculations. In step 4, we're going to use stat T-stats to sample, and this time it's with summary, because we already know the mean and standard deviation for each group. If instead we had two sets of data, like we'll have in problem 3, then we would use data instead of summary. Again, probably not a bad idea to list somewhere. Population 1 was the experimental group. List the mean, which was 14.8, the standard deviation, 12.5, and the size. And then do the same thing for the placebo group. It'll make it easier to get your information into and out of StatCrunch. The mean was 8.1, standard deviation 12.7, and was 60 for that group. Right. Like I wrote down, stat T to sample with summary. The first group, 14.8 for the mean, 12.5 for the standard deviation, and 55 for the size. For the second group, 8.1, 12.7, and 60. Don't check the box. Don't change the 0. The only thing we have to do is get to the right sign for HA, which is greater than. Click compute. And we get T equals 2.85, rounded to 2 places. That's a p-value of 0.0026. Is that low or high? That's low. That's below 0.01. We always compare it back to the level of significance, and it's lower than 0.01. If you don't see that, again, you can add a couple of zeros to the end of your p-value so that when you're comparing, the level of significance, 0.0100 to 0.0026, now we can see that the 0.0026 is the lower number. All right, what I want you to do is I want you to finish step 5. So you know that you've got a low p-value, so make your decision about HO, draw your conclusion about HA, and in maybe a minute or two, we'll go over that together. So if you're watching at home after the fact, the recording, pause it here, write up step 5, and then come back and we'll check you out. All right, so we'll pick it up from there. First, the right decision should have been reject HO. Because the p-value is lower than the level of significance, that's a low p-value. Whenever you have a low p-value, you reject HO. And then that also means that you do have enough evidence to support H1. Now, what are we supporting? The sign in H1 was a friendly sign. And that means that the wording in the problem will match the wording in the conclusion. And the wording in the claim is right here. The experimental group experienced a larger mean improvement than the control group. The experimental group experienced a larger mean improvement than the control group. The control group taking the placebo improved by 8.1 points. So we could expect anybody to improve by 8.1 points on average, but the group receiving the medication improved by 14.8 points. And our decision here, our conclusion says that that's significantly better. It didn't happen by chance. It's observable. And so the low p-value led to a strong decision, reject HO. That led to the strong conclusion. There is enough evidence to prove this. We're stating that we feel the experimental group had a larger mean improvement, meaning that this medication was effective. Any questions on problem 2 before we move on to one problem that has the data in it? Again, you can unmute yourself or you can type them in the chat. Now, for problem 3, before we begin, I've typed the data for this problem into StatCrunch and you have access to it. So let me show you how to get that. I'm just going to go back to the main StatCrunch screen, which I still have open here. So let me get rid of this tab. I'm going to go to my groups, Woodbury Math 21. Now, if you're not already in the group, instead of my groups, click where it said groups, type in Woodbury Math 21, and that'll take you to this group, which you can then join. Gosh, I forget what I called it, but I think it was Zoom 11.3. So let's try that. Yeah, right at the top, Zoom 11.3, click that data set, and you'll see the problems that we're going to use, the data that we're going to use tonight is already typed into StatCrunch for you. So I'll give you a moment to make sure that you can open that, or you can simply type them in as well. Make one column for lean meats and type those 8 values in there. Make another column for higher fat meats and type those 8 values in there. Now, last week we learned the pair difference test, and this problem really helps us to figure out how to spot the pair difference test versus the two mean test. What I noticed first is I have 2 sets of numerical data. That could either be a two mean test or a pair difference test. Then I see that both ends are the same. In both cases, we have sample sizes of 8. So this could still be a pair difference test. But what we're trying to figure out, is there any pairing going on here? Is the 844 in the first sample connected to the 843? They're not tied to the same person. And so, like, if those were identical twins and we had one of them eat lean meats and the other eat higher fat meats, well, there's a connection because they're identical twins. And so we could do a pair difference test on them, but we don't have that here. This is going to be two mean. And actually, I spoke a little too soon. It could also be a one mean test, depending on what the claim looks like. And here, the claim is comparing the mean for both categories. So we're comparing one group, lean meats, to another group, higher fat meats. And so that is what makes it a two mean test. If it said the mean consumption of calcium by those who eat lean meats is higher than 800 milligrams, then that's a one mean test. But I'm not going to give you an extra set of data that you're not going to use. But if you had these two sets, there are a couple of different tests you could do depending on what you were interested in. All right. First, in the claim, oops, let me do it this way instead. In the claim, no group is mentioned first, right? It doesn't say calcium for lean meats is the same as calcium for higher fat meats or vice versa. So it doesn't mention either group. When that happens, you should let the first group with data be group 1. So we'll let lean meat be group 1. Population number 1, lean meats. The null hypothesis, again, mu1 equals mu2. For H1, we'll also compare mu1 to mu2, but we need the right sign to use. And here, it just says that they're both the same. It doesn't say one's higher. It doesn't say one's lower. So without that direction, the greater or less than, H1, we fall back to not equal to. And when you see not equal to in H1, you want to be careful. When you write your conclusion, we have to write about the two groups being different from each other. Because if we write there is sufficient evidence that both categories have the same mean, that is HO. But what we're supposed to be showing is H1. That's why we say different for the not equal to part. Level of significance given as 0.05. This looks like a two mean test, but there are lots of conditions to check this time. For both the lean meat group and the higher fat groups, there's three conditions we have to check. We've got to check that 20N condition. We have to check the Shapiro-Wilk p-value needs to be above 0.05. And we need to make sure there are no outliers. The last two, we actually check when we're doing the calculations in StatCrunch. The first one we can check now. In both cases, these would be 20 times 8 or 160. See, these were children. Are there more than 160 children? Definitely. So that condition's locked in. We'll check the other two inside of StatCrunch. Stat T to sample, this time with data. The first column, the first sample is in the column that I called lean meats. The second sample is in the column I called higher fat meats. Don't check the box, leave the 0 in HO. For HA, because we're using not equal to, we're going to leave that alone too. So that part is the same as what we did for summary, but what's different is if we scroll down to the optional graphs and tables, you want to start at box plot and highlight all the way down to Shapiro-Wilk. And the two that we actually need are just the first and the last of those. Box plot is going to show us if there are any outliers, so we can check this last condition. And the Shapiro-Wilk normality test will help us check that middle condition. Compute. And let's start with the Shapiro-Wilk results, which are down here at the bottom. We're interested in the p-values. So for the lean meats, p equals 0.8755, and that's above 0.05. So that one works. For the higher fat, p equals 0.2248. That is also above 0.05. So that condition is good. To check for the outliers, I need to move over one screen. There are the two box plots. There are no outliers shown. So now all the conditions are good. And what that tells me is that my calculations here, I can use, right? I can do this test as a two mean test. So first, the test statistic, T equals negative 1.89. That means that the lean meat group was about 1.9 standard deviations lower than we expected it to be. The p-value, which is the chance of this happening by random chance, is 0.0807. And when we compare that back to the level of significance, this is a high p-value. So first, when it comes time to the decision, a high p-value means fail to reject HO. That means we assume that the means were equal and we couldn't prove that that was false. Like we assume that the defendant is innocent and we couldn't prove that that was false. In other words, that the defendant is guilty. That's what's happened here. When you don't reject HO, that means there is not sufficient evidence to support that. And here's where you've got to be careful. I think a good strategy is always to look at that sign in H1 before you decide what you're going to write in your conclusion. And here, I need to rewrite this claim in terms of being different. That the mean calcium consumption for both categories instead of where it says is the same, I'm going to write that it is different, because that's what that not equal to sign means in H1. Now, if when you did the homework, the activity for 11.2, there are actually 2 times that happened in problems. I think it was problems 2 and 3. H1 was not equal to, and so your conclusion had to be about 2 things being different from each other rather than being the same as each other. So when that H1 contains the not equal to sign, that should set off a little alarm for you that I need to be careful with the conclusion. And by being careful, that means that you need to write it in terms of the first group being different from the second group. All right, so that's one of each type. We saw a 2 proportion problem in example 1. Then we saw a 2 mean problem where we use summary information in example 2. And then finally 2 mean with data in example 3. And again, the big difference between problems 2 and 3 is that when you have data, you have more conditions to check. All right, any questions on any of these 3 for me? All right, I'm going to take that as a good sign. I'm going to stop the recording and we'll just wrap it up after that.